Okay, let's give you guys some more practice now. So let's say I've got a semicircle here. I'm going to create a box inside here, inside this semicircle here. So it could be this box here. Remember that this box here is symmetrical along the y-axis, meaning that this length here will always be the same as this length here. Okay. Well, I could create this box, or I could create this kind of a box. I want to maximize the area of my box. So how can I maximize the area of my box? So you got to think about this, because there are lots of ways of doing this, because you could vary x here. Ultimately, you want a graph of the area versus something. Okay, and there are lots of ways of doing this. This something here could be x here, so you could vary x from here to here. Okay, so you could slide x back and forth, or you can create, or you could create a graph of area versus height. Okay, where you could vary this height. But for well, you can do it whichever way you want. But for me, I just want to do something different. So let's vary it. So vary the angle here, theta. Okay, so this box could be down here. So don't forget, when theta is, let's say when theta is here, okay, our box would be this one here. Our box will be this one here. Okay, so there are lots of ways of doing this. Ultimately, you want a graph of A versus something, but we could well for our something here, I'm going to vary theta. So our domain here, area versus theta. So the domain for our problem here will be 0 greater than 0. So theta has to be greater than 0, but less than 9 pi over 2. Okay, we're going to work in radians. Well, there are lots of ways of doing this, but for me, I'm going to use area versus theta, the angle here. Okay, so what's the biggest area that I can fit in this semicircle? Okay, so press pause and have a go. Okay, so to do this here, hang on. We're going to we're going to vary theta here. So the height will be given by this, and the from here to here will be given by this. So when you look at our box here, hang on, this will be our box here, straight down, hang on, straight down. So this here will be our box. So the overall length from here to here will be given by double this. So this times 2. So the 2 times with the 2 here, that will be 4 cos theta, and then we've got to times it by the height. So that will be times 2 sine theta. So this here is our area, and then you can merge these two together. That will give you 8. Well, anyway, that will give you 8 cos. Well, the area will be given by this. Okay. So now when we get to this stage here, what we in effect have is a graph of area versus theta here. Okay. So now have a quick glance to see what's going on. When theta is really small, you can see that the area is going to be really small. When theta is, let's say pi over 4 at 45 degrees here, pi over 4. The area you can see is bigger than this area here when theta is small, or when theta is near pi over 4, which is near 90 degrees. The area here will be tiny. Okay, so we know that at the two extremes here. So when you get to this stage here, hang on, when you get to this stage here, you in effect have a graph of A versus theta. The point that I'm trying to make is that when theta is 0, and remember pi over 4 here, this here is our domain really, between 0 and pi over 4. When theta is near 0, it's going to be tiny, somewhere around here, and when it's near 90 degrees or pi over 4 radians, it's going to be very small. So we know that it's going to, maybe it would do something like this. But the point here is that this bit here would be very small. This bit here would be very small. So we want to find out when the gradient of this will be 0. Okay, we just remember that you can't just, once you've got the area versus theta, you can't just blindly differentiate it and then find out where the gradient is 0. You need a sense of what's going on. Well, we've developed a sense of what's going on by looking at when theta is 0, near the 0, and when theta is near pi over 4. Okay, so we by us looking at that, we had a sense of what's going on around these two extremes. So we can now just differentiate it. So let's differentiate it. It will give you this. So here, when you look at this here, visualize as one block here and one block here. So you've got to use the product rule. So the product rule is differentiate this, leave this the same. Okay, and then later leave this the same, differentiate this. That will then give you this. Okay, and then sine theta times sine theta, that will be sine squared, and so on here. So this thing here will become this. Okay, and then let the gradient be 0. Let dA by d theta be 0. That will then take you to here. And then when you get to here, you want to find out theta when add this to both sides. That will then give you this. And then divide both sides by 8. That will then give you this. And then square root both sides. That will then give you this. So you see the gradient, our dA by d theta will be 0 when you make this the same as this. Okay. So when will this be the same as this? Well, if you look at it, when will it's like you asking yourself, when will the height of a unit circle, let's say you've got a circle here, when will the height be the same as the, so this thing here, when you're here, when will the height, which is sine theta here, when will the height be the same as the width here? You see, when it's at pi over 4 or 45 degrees, that's when the height will be the same as the width here. So this thing here, this will equal this when theta equals pi over 4. Okay, so your biggest box will be when theta is pi over 4. Okay, so this is the formula for the area, and then when you put pi over 4 into that thing, the area will be given by this. Okay, so going back to our original problem. Hang on. Going back to our original problem here. You see, when you make theta to be 45, when you make theta to be pi over 4 degree, when you make theta to be pi over 4, that's when you will have your biggest box here. Hang on. This is when you will have your biggest box here. This will be the biggest box here. Okay, and by the way, this from here to here would be 2 cos pi over 4. Okay, because the hypotenuse here is 2. The hypotenuse here is 2. So this distance here will be 2 cos pi over 4. Okay, but this is sufficient when you state theta to be pi over 4. Okay, that will give you your biggest box. Okay.